Hello, so in this video we're going to be talking through vector equations of lines. Now just remember, we're happy with working with equations of lines in 2 dimensions, like the y equals mx plus c, or any kind of general form that you want to write your straight lines in. However, lines can also happen in 3 dimensions as well. For example, if one of the lines is my arm and another line is my other arm, then you can see that these 2 lines can kind of exist in 3 dimensions. Now, there are formulas for working with lines in 3 dimensions, but they're a little bit awkward. So it makes sense to work with them in terms of vectors. Now you remember that when we write a vector equation of a line, we need 2 parts. We need, first of all, a kind of a direction vector. Now this is the kind of direction vector which I'm talking about. So it's always the number that is multiplied by some scalar. That will basically tell you the direction which the line is happening in. But of course we also need to determine how high or low in 3-dimensional space that line is as well. So that's the reason why we add on the position vector as well. So really, the vector equation of a line is always made up of 2 parts. It's a direction vector, telling you what direction the line is in. And of course the reason why we multiply by a scalar is because we can move along any multiple of that direction vector. For example, I might want to move 2 times in that direction, or 4 times in that direction, or 1,000,000 times in that direction to get to some general point. But I also need a position vector to actually get me onto the line in the first place. In other words, to tell me how high or low that line is. Okay. Now I've been given 2 lines here, and I've numbered them R1 and R2. Now just remember, R, so this thing here, is the position vector of any general point that I know lies along the line. And I've just called it R1 and R2 just to establish that this is line 1 and line 2. Okay, and I've been asked to show that these points intersect, so these 2 lines intersect, and I've been asked to find the point of intersection. Okay, fine, fantastic. So in order to do this, I can just simply set the components of each of the vectors together. Because I'm saying if they intersect, which I'm told they do, but I'm going to assume that they don't in order to show it. Okay, so if they intersect, then what I'm literally saying is that there should be a point which lies on line 1 which is equal to a point which lies on line 2. So in other words, there should be a point, one unique point, which lies on both lines. In other words, can I find a position vector which will get me to the same point which lies on both lines? Okay. So in order to do that, I'm just going to set these 2 things equal to each other. So I'm simply going to look at the components, so the I, J, K components of each vector and set them equal to each other. So I'm going to take 7 plus lambda lots of -2. So that's going to be 7, I'll do it in blue, 7 minus 2 lambda, and that should be equal to 8 plus mu times 1, so 8 plus mu. And then if I look at the j components, well, it'll have -3 plus 5 times lambda, should be the same as the j components of the second line, which is -1 minus 4 mu. And then there should also be a component, should also be the j components equal to each other, so 1 plus lambda should be equal to -1 and then plus 0 mu, so just -1. Okay. Now my job is to solve this system of equations here in order to find a lambda and mu which works in all 3 equations, and then I should be able to sub it in to find the point of intersection. Okay, so let's do it. So first of all, I think this is the easiest one to try and solve, the bottom equation. So 1 plus lambda equals -1. Because if I solve this, I get lambda is equal to -2. I just take away 1 from both sides. So that's nice and easy. Don't have to faff around with an equation with 2 variables in. I can just find lambda equals -2. Now using that, I can stick that into one of the other equations, I think the top one, in order to find what mu is equal to. So now I know lambda is equal to -2. I get 7 minus 2 times by -2, because I'm subbing in lambda equals -2 now, and that should be equal to 8 plus mu. Well, okay, if I solve that then, mu should be equal to, well, 7 take away 2 times -2, that's the same as 7 plus 4, that's 11. And if I take away 8, that's going to leave me with 3. So therefore I have mu equals 3. Now always check, because I need to show that they intersect. In order to check that, I'm going to make sure that mu and lambda are consistent with that equation. In other words, the equation which I haven't used. So if I sub in lambda equals -2, then I can just look at the left-hand side. So if I look at the left-hand side equation, I have -3 plus 5 times by -2. Well, okay, -3 take away 10, that's equal to -13. And it should happen that the right-hand side is equal to the same thing. So let's have a look. Well, -1 minus 4 times by 3, Well, okay, 4 times by 3 is 12. That's going to be negative 12. Then if I take away 1, lo and behold, that's equal to negative 13. So because the left-hand side equals the right-hand side, then that means that it works, okay? But I've also been tasked to find the point of intersection. So just remember, what do these two equations of lines tell me? Well, the R, so either R1 or R2, okay, they represent the position vector of a point which lies on the line. So if I want to get to any point which lies on line 1, I just need to stick in a value of lambda, and then that will get me to any point which lies on line 1. Similarly, to get to any point which lies on line 2, then all I need to do is stick in some value for mu, whatever value I like, and that will get me to a point which lies on line 2. So what I'm going to do is I can either use lambda equals negative 2 or mu equals 3 into either one of these two equations to find the point of intersection. It should be that they find the same point. I'm going to use mu equals 3, so I'm just going to use the second equation. And I can say, okay, when mu is equal to 3, then I can find that the position vector of the point of intersection should be equal to, well, I have 8 plus 3 times 1, because of course I'm just substituting mu equals 3 in there now. So 8 plus 3 times 1, that's equal to 11. Negative 1 plus 3 times negative 4, so 3 times negative 4 is negative 12. And then if I take away 1 from that, that's equal to 13. And then finally, negative 1 plus 3 times 0, that's just equal to negative 1. Okay? So therefore, the point of intersection should be 11, 13, and negative 1. Okay, so the point is 11, 13, negative 1. The position vector is given as a column instead. And if I also wanted to just check that, I could also stick in lambda equals negative 2 into this line, vector equation of a line, and I should still get exactly the same point out. Okay? Okay, so let's move on. Let's have a look at question 2. So again, we've been given two lines, and I'm just sort of numbering them line 1 and line 2, and I'm also numbering the position vector of a point which lies on the line as R1 and R2, okay, respectively. So in this case, I've been given the two lines in terms of IJK notation. That's fine, it's still exactly the same idea. I still have a direction vector, and I still have a position vector, okay? And in this case, I've been asked to establish whether line 1 whether line 1 and line 2 intersect, whether they're parallel to each other, or whether they're skew. Okay, so this is the order which I want you to check a question like this. So if you've been given two vector equations of lines and you've been asked to determine whether they are parallel, whether they're intersecting, whether they're skew, this is the order that I want you to check in. Number 1, I want you to check if they are parallel. Now the way to check that they are parallel is the easiest one, which is why I'm asking you to do this one first, okay? Because to check whether they're parallel, just remember the vector equations are made up of two parts. The first part, which I'll put in red, is a position vector. That just simply tells me how high or low in three-dimensional space that line is, okay? If you like, that's the y-intercept. That's telling me how high or low that line is, okay? Relative to the origin position. The second component, which I'll put in blue, are the direction vectors. Now the direction vectors are telling me which direction that line is facing in, okay? Those are the gradients of the lines, if you like. Those are the unique identifiers that make sure that the line faces in the right direction, okay? So if they're parallel, it should be that they're facing in the same direction. In other words, the direction vectors should be kind of similar to each other. i.e., if they want to be parallel, they just need to be off by some scalar multiple. So for example, if the second direction vector is just like twice whatever the first direction vector is, then that's fine because they're still going to be facing in the same direction. Remember, in order to be parallel, they just need to be some scalar multiple of each other. So let's check this. So basically what I'm saying is that 2 should be equal to some constant of 5, and the same thing with the j directions, that 5 should be some constant times by negative 3. And the same thing with the k direction, so negative 3 is equal to k times by negative 4. Now basically, if I solve these and if I find that the constant, the scalar multiple, is the same for each of the ijk components, then that means they must be parallel. So let's have a look. So if I look at k for the first one, for the I components, I find k is equal to 2/5, or 0.4. In other words, if I multiply the 2 by 0.4, I'll get 5, okay? Now let's just check to make sure it's consistent for the second, the j components. I get k is equal to negative 5 over 3. Ah, well, okay, they're not the same value of k, therefore I know they're not parallel because I cannot find a common scalar multiple for each of the I, j, k components. But let's just check for k, just for the k components anyway. So k must be equal to, well, this is equal to 3/4. So again, okay, so I'll just write, so no scalar multiple so therefore they're not facing in the same direction, okay, so they are not parallel, okay, and that would be enough. Just kind of showing a working very, very similar to this. Perhaps you might want to choose a different value to k because of course we've already got k as the component vector. Didn't think about that at the time, but it's still fine, okay? It's still kind of same principle. Maybe it's just a different value of k for your scalar multiple, but effectively just checked with your direction vectors, see whether they're facing in the same direction. And you can do that by checking whether they're scalar multiple of each other. In this case, they're not parallel. So the next thing I want you to check is whether they are intersecting. So number 2, let's check to see whether they're intersecting. Well, we've just seen a question in the last example where we had to show that things were intersecting. So in order to do that, I just simply compare the I direction of both the position and the direction vectors, put it together for the line 1. So I'll just quickly do that. So that's going to be 4 plus 2 lambda. And that should be equal to the I direction of line 2. So 3 plus mu lots of 5. So 3 plus 5 mu. Sorry, that's equal to 3 plus 5 mu. I put it in the wrong place. Okay? And then I do the same thing for the j component. So again, -1 plus 5 lots of lambda. So -1 plus 5 lots of lambda for line 1. And for line 2, I end up with -2 minus 3 mu. So -2 minus 3 mu. Okay? Now if I do the same thing for the k directions, I end up with 3 minus 3 lambda for line 1. So 3 minus 3 lambda should be equal to 1 minus 4 mu. So 1 minus 4 mu for the k directions for line 2. And it should be the case that if they are intersecting, I should be able to find a value of lambda and mu which works in all 3 equations. Okay? So let's check it out. So I'm just going to solve these. Now, to make my life a little bit easier, I'm just going to rewrite them. So I'm just going to have a look at the first 2 equations. So if I have a look at equation 1, I should be able to rewrite that as, let's see, 2 lambda minus 5 mu is equal to, let's have a look, 3 take away 4, that's -1. And if I rewrite the second equation, I end up with 5 lambda plus 3 mu is equal to -2 plus 1, that's equal to -1, okay? So therefore, if this works, I should just basically be able to multiply these things up. So let's make sure that we can do an elimination, just simultaneous equations now. So I'm going to multiply the first equation by 5 to get 10 lambda, e minus 25 mu is equal to -5. And if I multiply the second equation by 2, I end up with 10 lambda plus 6 mu is equal to -2. And if I want to get rid of the 10 lambdas now, I can just subtract them from each other. So -25 minus 6 mu, that's going to give me -31 mu, is equal to, let's be careful, -5 take away -2, that's going to be the same as -5 plus 2, that's going to be -3. Which means that the value of mu from those first 2 equations should be equal to 3 over 31. Okay? Now it's a bit awkward, but that's fine. If I just carry on going with this, I should be able to find lambda. So in order to find lambda, I'm going to be working with the top 2 equations. So don't go for the third one just yet. Rule that one out, okay? Only work with the top 2 equations. So in fact, I'm just going to use that one to see what lambda is equal to. So 2 lambda minus, well, I've got 5 lots of mu, so that's minus 15 over 31 should be equal to -1. Well, okay, if I solve this, I end up with 2 lambda is equal to, well, let's see, -1, stick this in my calculator, -1 plus 15 over 31, that should be equal to -16 over 31. Which means when I divide by 2, then I end up with lambda is equal to -8 over 31. Okay, so that's my value of lambda. So I've got mu equals 3 over 31, lambda equals -8 over 31. Now let's just quickly check in my last equation, in other words, the one that I didn't use up here, this one here, to see whether mu and lambda is consistent. So all I'm just going to do is just check the left-hand side first of all, remembering that, of course, I should write this down. Mu was equal to, what was it? 3 over 31. and lambda was equal to negative 8 over 31. So let's check the left-hand side first of all. What do we get? Well, okay, the left-hand side, we get 3 minus 3 lots of lambda. So this is going to be, let's stick it in a calculator because I can't be bothered, 3 plus 24 over 31. That's going to give me 117 over 31. So that's what's coming out on the left-hand side. If I look at the right-hand side, so in other words, 1 minus 4 times mu, well, that's going to be 1 minus 4 times mu, that's going to be 12 over 31. Okay, well that comes out as 19 over 31. So because I can say that the left-hand side is not consistent with the right-hand side, because remember that these mu and lambdas which I found over here were only consistent with the top 2 equations. So mu and lambda works in the top 2 equations, but I also need it to work in the final equation if these things are going to be intersecting. So because when I stick in my mu and lambda into my bottom equation, in other words my k components, I don't find that they work. I don't find they're consistent. Okay? So therefore I can say that because there is not a consistent value of mu and lambda, or values I should say, of mu and lambda, then it is not intersecting. Remember that in order for it to be intersecting, we need to find a value of mu and lambda which work in all 3 equations. In this case, they don't work in all 3 equations, therefore they're not intersecting. Okay? So actually, this is all my work done. This is the reason why I say you need to answer these questions in this order. Number 1, we checked for parallel, and we did that by making sure that we had sort of a scalar multiple with the direction vectors. In this case, we didn't find a common scalar multiple, therefore they're not parallel. Then we checked intersecting, so basically we solved this equation, we solved this system of equations. If we find a value of mu and lambda which work in all 3 equations, they're consistent, then we can basically say they're intersecting. In this case, they're not intersecting, so therefore the skew check is actually very easy. We've done all the work, okay? We can just simply say, since they are not parallel, so line 1 and line 2, because line 1 and line 2 are not parallel, because we've checked the direction vectors, and they are not intersecting, we've just checked that, we've just basically set up our system of equations and tried to solve them, and we couldn't find a value that works in all 3 equations, then that must mean there's only one thing left for them to be. It means they must be skew. Now just remember, skew must mean that these 2 lines basically miss each other. Okay, so in 3-dimensional space, they don't intersect, so they don't cross, and they're not traveling in the same direction, therefore they completely miss each other. So if my 2 lines are my arms, they completely miss each other. Okay, so always do it in this order. Parallel, check the direction vectors, see if there's a common scalar multiple. Then for intersecting, set up your system of equations, so set I equal to each other, j equal to each other, k equal to each other. If you can find a common value of mu and lambda which work in all 3 equations, you've got your intersection point. If you haven't, it must mean they're not intersecting, they're not parallel, they must be skew. Okay, so nice and easy.